Hi, I am a tutor in Uplatz. Today we are going to discuss about automotive, electric and automotive electronic systems part 2. Electronic diesel control system overview. Electronic control of the diesel engine enables precise and differentiated modulation of fuel injection parameters. This is the only means by which a modern diesel engine is able to satisfy the many demands placed upon it. Electronic design control is subdivided into three systems blocks: sensors, setpoint generators, ECU, and actuators. Requirements: the lowering of fuel consumption and exhaust emissions, NOx, CO, particulates combined with simultaneous improvement of engine power, output, and torque are the guiding principles of current development work on diesel engine design. Conventional indirect injection engines (IDI) were no longer able to satisfy these requirements. State-of-the-art technology is represented today by direct injection diesel engines (DI) with high injection pressures for efficient mixture formation. The fuel injection system support several injection processes: pre-injection, main injection, and secondary injection. These injection processes are for the most part controlled electronically. Pre-injection, however, is controlled mechanically on UAS for cars. In addition, diesel engine development has been influenced by the high level of driving comfort and convenience demanded in modern cars. Exhaust and noise emissions are also subject to the ever more stringent demands. As a result, the performance demand of the fuel injection and management system has also increased, specifically with regard to high injection pressures, right, shaping, pre-injection and deepness, second injection, adaptation of injected fuel quantity, boost pressure and start of injection at the respective operating status, temperature dependent excess fuel quantity, load independent idle, speed control, controlled exhaust gas recirculation, cruise control, tight tolerance for start of injection and injected fuel quantity, and maintenance of high pressure over the service type of the system, long-term performance, support of exhaust gas treatment systems. EDC system blocks, sensors, and setpoint generators, actuator pedal sensor, air mass sensor, rail pressure sensor, boost pressure sensor, temperature sensor, air and coolant, and lambda oxygen sensor, wheel speed sensors, cranks, shaft and camshaft, brake switch, clutch switch, ignition switch, loop control, CAN, and fault diagnosis. ADC function processor, RAM, flash, EEPROM, and monitoring module and other switching circuits make the ECU. And actuators are injectors, intake that switch off, boost pressure actuator, exhaust gas recirculation actuator, throttle lower actuator, AC compressor, auxiliary heating, radiation fan, rail pressure control valve, electronic shut-off valve, and diagnostic lamp. Conventional mechanical RPM control uses a number of adjusting mechanisms to adapt to different engine operating statuses and ensure high quality mixture formulation. Nevertheless, it is restricted to a simple engine based control loop, and there are a number of important influencing variables that it cannot take account of or cannot respond quickly enough to. As demands have increased, EDC has developed into a complex electronic engine management system capable of processing a large amount of data in real time. In addition to its pure engine management function, EDC supports a series of comfort and convenience functions. Example, cruise control. It can form part of an overall electronic speed control system driven by wire as a result of the increasing integration of electronic components. Complex electronics can be accommodated in a very small space. Operating principles: electronic digital control is capable of meeting the requirements listed above as a result of microcontroller performance that has improved considerably in the last few years. In contrast to diesel engine vehicles with conventional inline or distributed injection pumps, the driver of an EDC controlled vehicle has no direct influence, for instance, through the accelerator pedal and wound cable upon the injected fuel quantity. Instead, the injected fuel quantity is determined by a number of increasing variables. These include driver command, accelerator pedal position, operator status, engine temperature, intervention by other system, example TCS, effects on exhaust emissions, etc. The ECU calculates the injected fuel quantity on the basis of all these influencing variables. Start of injection can also be varied. This requires a comprehensive monitoring concept that detects inconsistencies and initiates appropriate actions in accordance with the effects. Example, torque limitation or limp mode in the ideal speed range. EDC therefore incorporates a number of control loops. Electronic DC control allows data communication with other electronic systems such as the traction control system, electronic transmission control, ETC, or electronic stability program ESP. As a result, the engine management system can be integrated in the vehicle's overall control system, thereby enabling functions such as reduction of engine torque when the automatic transmission changes gear, regulation of engine start to compensate for wheel slip, etc. The EDC system is fully integrated in the vehicle's diagnosis system. It meets all onboard diagnosis and European onboard diagnosis requirements. System blocks, electronic disk control is divided into three system blocks: sensors and setpoint generators, direct operating conditions, example engine speed and setpoint values, example switch position. They convert physical variables into electrical signals. The ECU processes the information from the sensor and setpoint generation in mathematical computing process, open and closed loop control algorithm. It controls control the actuators by means of electrical output signal. In addition, ECU acts as a interface to other systems and to the vehicle diagnosis system. Actuators convert the electrical output signals from the ECU into mechanical variable, example terminal void, neutral, left. Data processing, the main function of the electronic diesel control is to control injected fuel quantity and the injection timing. The common rate accumulator injection system also controls injection pressure. Furthermore, on all systems, the engine ECU controls a number of actuators. The EDC function must be matched to every vehicle and every engine. This is the only way to optimize component interaction. Schematic, you see the example of a current regulator, L actual, L set point is set, and it goes through a series of control action and comes to the PW set point. Basic sequence electronic diesel control, fuel control circuit 1, fuel injection component, fuel control circuit 2, engine, diversion via driver, triggered fuel injection control, triggering of the fuel injection components. It consists of a CAN interface through which data exchange with other systems, transaction control system, transmission control system, AC control, etc. happens. The central one is the sensors and setpoint generators, actuators, sensors, speed sensors, and switch, to which a driver commands, a driver cruise control and engine brakes, etc. comes, and to the output control and integrating of the remaining actuators happens through CAN interface. Sensors get information from cylinder charges, control system, supercharging, exhaust gas recirculation, and the control actuates pneumatic converter, continuous operation, brake system, fan and blow tank control. The engine gets the fuel injection components, inline fuel injection pumps, distributor type fuel injection pumps, unit injector unit pump, common rail high pressure pump and injector nozzle, holder, and nozzles. The control unit evaluates signals sent by the sensors and limits them to the permitted voltage level. Some input signals are also checked for pulsability. Using this input data together with stored program maps, the microprocessor calculates the position and duration for injection timing. This information is then converted into a single characteristic which is aligned to the engine's piston strokes. This calculation program is done the ECU software. The required degree of accuracy together with the diesel engine's outstanding dynamic response requires high double computing power. The output signals are applied to the driver stages, which provide adequate power for actuators. For instance, the high pressure solenoid valves for wheel injection, exhaust gas circulation booster or boost pressure actuator. Apart from this, a number of other auxiliary function components, for example, low relay and air conditioning system, are triggered. The driver stage diagnosis functions for the solenoid valves also detect faulty signals characteristics. Furthermore, signals are exchanged with other systems in the vehicle via the interfaces. The engine ECU monitors a complete fuel injection system as a part of a safety strategy. Fuel injection control table 1 provides an overview of the EDC functions which are implemented in the various fuel injection systems. Figure 4 shows the sequence of fuel injection calculation with all functions, a number of which are optional extra. These are can be activated in the ECU by the after-sales service when retrofit the equipment is installed. In order that the engine can run with optimal combustion under all operating conditions, the ECU calculates exactly the right injected fuel quantity for all the conditions. Here, a number of parameters must be taken into account on a number of solenoid valve control distributed type injection pumps. The solenoid valve for this injected fuel quantity and start of injection are triggered by a separate pump ECU. And the table shows the overall view of EDC variants for motor vehicle fuel injection systems. Inline fuel injection pumps, elites control distributor type injection pump, solenoid valve control distributor injection pump, unit injection system and unit pumps system, and common drive system. The functions are injected fuel quantity limit, external torque intervention, driving speed limitation, cruise control, attitude correction, boost pressure control, idle speed regulation, intermediate speed regulation, active surge damping, BIP control, intake port setup, electronic immobilizer control, re-injection, control unit, AC switch off, auxiliary coolant heating, smooth running control, fuel balancing control, fan activation, EGR control, stator injection control with sensor, cylinder shut off, increment angle learning, increment engine rounding. Calculation of fuel injection pressure issue requests the calculations accelerated sensor input by the driver and input from the other system, ABS, ESR, CF into CAN. It goes to the external torque intervention, and cruise control time speed is another input, and speed selection of desired injection fuel quantity. Injected fuel quantity limit is checked, and idle speed control and fuel balancing control is affected. Then start switch and variable operation happens. Smooth running regulator is one of the input for that. Then start quantity is another input. Then granularity metering pump map and control for start of the injection and start of the delivery. All this comes to the activations and activation of timing devices, activation of solenoid valve and signal pump ECU are affected. Torque control. Torque control EDC system, the engine management system is continually being integrated more closely into the overall vehicle system, vehicle dynamic systems, comfort and convenience systems, cruise control and tempo mat, and transmission control, electronic diesel control via the CAN bus. Apart from this, much of the information registered are calculated in the engine management system must be passed on to the other issue via the CAN bus. In order to be able to incorporate ADC even more efficiently in a functional alliance with other ECUs and implement other changes rapidly and effectively, it was necessary to make radical changes to the newest generation control. These changes resulted in torque control EDC, which was introduced with the EDC 16. The main feature is changeover the model interfaces to the parameters as commonly encountered in practice in the vehicle. Engine characteristics essentially an engine's output can be defined using the three characteristics power P, engine speed N, and the torque M. Figure shows compares typical curves of torque and power as a function of engine speed of a two-diesel engine. Basically speaking, the following formula applies P is equal to pi N. M is the M into M. It is sufficient, therefore, for example, to specify the torque as a reference variable while taking into account the engine speed. Engine power then results from the various formula. Since power output cannot be measured directly, torque has turned out to be a suitable reference variable for engine management. Torque, when accelerating, the driver uses the accelerated coil sensor to directly demand a given torque from the engine. Independently of the driver's requirement, other external vehicle systems submit torque demands via the interfaces resulting from the power requirements of the particular component, example, air conditioning system or train tire. Using this torque requirement input, the engine management system calculates the output engine torque to be generated and controls fuel injection air system actuators accordingly. This has the following advantages. No system has direct influence on the engine management, boost pressure, fuel injection, peak flow. The engine management can thus also take into account other higher level optimization criteria for external requirements, exhaust gas emission, fuel consumption, and then control the engine in the best way possible. Many of the functions which do not directly concern the engine management system can be designed to their function identically for diesel and gasoline engines. Expansion systems can be implemented quickly. Example of the torque and the power output curves as a function of engine speed for two car diesel engines with approximate 2.2 and engine displacement are shown here. Power output and torque. Engine speed is the x-axis. Sequence of engine management, the setpoint bonds a process for the ECU in order to fulfill other assignments efficiently. The engine management systems control functions also require a range of sensor signals and information from the ECU in the vehicle. Propulsion torque, the driver's input, that is the signal from the accelerator sensor, is interpreted by the engine management system as the request for the propulsion torque. The inputs from the cruise control and the vehicle speed limiter are processed in exactly the same manner. Following this action of desired propulsive torque, should the situation arise, the vehicle dynamic system, TCS ECP, increases the desired torque value when there is a danger of wheel lockup and decreases it when the wheels show a tendency to spin. Further external torque demands, the drivetrain torque adaptation must be taken into account. Drivetrain transmission ratio. This is defined for the most part by the ratio of a particular gear or by the torque converter efficiency in the case of automatic transmissions. On vehicles with the automatic transmission, the transmission control stipulates the torque demand during the gear shift. This is reduced in order to produce comfortable, smooth gear shift, thus protecting the engine. In addition, the torque required by other engine-powered auxiliary system, example, air conditioning, compressor, or row pump, is determined. This torque demand is calculated either by the auxiliary system themselves or by the engine management system. The calculation is based on the required power and engine speed, and the engine management system adds up the various torque requirements. The vehicle drivability remains unchanged, notwithstanding varying requirements from the auxiliary systems and changes the engine operating stage. Internal torque demands at this stage, the ideal speed control and the active surge damper intervene. For instance, if demanded by situation in order to prevent mechanical damage or excessive smoke due to the injection of too much fuel, the torque limitation reduces the internal torque demand. In contrast to previous engine management system, limitations are no longer only applied to the injected fuel quantity, but instead depending on the requirement also to the particular physical quantity involved. The engine losses are also taken into account. Friction drive for the high pressure pump The torque represents the engine's measurable effects to the outside. However, the engine management system can only generate these effects in conjunction with the correct fuel injection together with the correct injection point and the necessary marginal conditions as applied to the air system. Example, boost pressure and less gas recirculation. The required injected fuel quantity is determined using the current consumption efficiency. The calculated fuel quantity is limited by a protective function. Example, protection against overheating, and if necessary, can be varied by smooth running cutoff. When the engine start, the injected fuel quantity is not determined by external inputs such as those for the driver, but rather by separate quantity control function. Actuatorically, the resulting set point value for the injected fuel quantity is used to generate the triggering data for the injection pump and or the fuel injector and for defining the optimum operating point of the intake air system. Thank you.